computational learning theory, and with the examples of concept learning, uh, we can understand some of the basic issues which are involved in this particular framework. So one of the characterization of a learning model, which is that no, probably approximately correct learning model. So which means that no, you may have your level data error free. That means if you have a consistent hypothesis, your training error will be also zero. But what happens that that hypothesis may not be exactly representing the concept or target function. So in that case, there would be some instances in your instance space where they will differ. That means you will have an error which we call true error with respect to, if I consider the whole instance space, or we name it also as a population. So in the whole population, if we apply your hypothesis for predicting the levels, then there would be error from its true levels. So we call this error, we represent this error in this with this notation. You see that it is an error. Actually, later on we will call it test error. So it's a true error. That's a term we are using because we are considering it is the over the whole population. So you can probabilistically you can define this error as the probability that your functional value of the target function is not the same as that of the hypothesis. So that is the theoretical definition of this error in this case. It's a probability of the difference of values with respect to that. Now, with this definition of an error, we can define a type of learning models or type of learning where we try to keep a bound on that particular type of true error. Say we'd like to get a bound on that true error. So your learner should give you a model which will have this property that this error would be bounded. Now, once again, there is always a kind of probabilistic interpretation. So you may not ensure that your learner will always give that kind of model. We call that kind of model is probably approximately correct learning model when the training error is zero and also true error is bounded by certain value. The probability is that probability of error is bounded. And also when you are learning, so there are some other aspects. So as you understand that if you have more samples, then you will have a better chance of getting close to the target concept, true target concepts. That is one thing. But no, how long will it take? That is another issue. So when you are learning something, it is basically you are searching over the hypothesis space. Now, if you go on enumerating every hypothesis, then of course you see that that is not very practical. If your hypothesis space is also exponential of the size of your input representation of the dimension, input representation, or the size of the hypothesis itself. So there are certain other constraints which we impose that to get a practical solution, practical learning model or learning scheme under this characterization. So that is what we will be defining next. So we say that a target concept is PSE learnable, that if I consider in your representation, so any kind of target concept, if you look at the over the distribution of the instance space, so there are two things. One is that your true error, that should be bounded by epsilon, since you want it should be less, at least it should be less than half. That is why it is desirable. On the other hand, the probability of getting a hypothesis, a version space, so that now all consistent hypotheses in that version space satisfy this property, they are all bounded by this epsilon. So probability of that should be at least 1 minus delta. And this computation should be in polynomial order of some of the input parameters. So these are the three things that you should note in this definition. So I'll be just providing you the definition, the theoretical statement itself, and these are the things you will note. So this is what. So for any target function in that target function space, you will have that there exists a learner. This learner should, with probability at least 1 minus delta, outputs a hypothesis H in the hypothesis space such that true error is bounded by epsilon in time that is polynomial in 1 by epsilon, 1 by delta, n is the number of training samples, and size of the corresponding concept itself. So size is, for example, in our specific case, the example case what we discussed, that all Boolean literals, and it's a 6-dimensional representation there when you are representing a concept. Okay, so 6 is the size, you can say, unit of 6, you can say. Now there are some of the things when we say, when we try to get a learning scheme as PSE learnable, or a learner as PSE learnable, we would like to know that what is the minimum number of training samples that would ensure that it is PSE learnable with some of the parameters like epsilon, in terms of epsilon and say delta. Also the size of the hypothesis is also. So size of the hypothesis also determines the size of the hypothesis space, right? So in terms of that, how many training samples would be required so that with certain high probabilities that delta? So 1 minus delta. So number of samples for a PSE learner, that is important. Or is the same thing. How many samples required so that the version space consists of any consistent hypothesis bounded by an error epsilon. Actually, all hypotheses in a version space has to be this. For a target concept C having such property, then that version space is called epsilon exhaustive version space. So every hypothesis in the version space has this property. So a theorem of epsilon exhausting the version space is that given finite hypothesis space, finite dimensional hypothesis, or that is finite size of hypothesis space of a target concept C, and M is their training examples independently randomly drawn forming data G. So D is your set of training samples which has in the form of instance and its level. So for any this epsilon parameter, of course epsilon here is bounded by 1 because it's a probability, but desirable value of epsilon should have been half for a PSE learnable things. So it's a theorem that probability of the version space is epsilon exhausted is less than this particular thing, that size of the hypothesis space into e to the power minus epsilon into m, which is the number of training samples. So this is an interesting theory, interesting indications that it shows that if you increase your training example, then so then the definition of epsilon exhaustive. So let us see the proof, then we'll see the implications later. So the proof is that for any hypothesis H, suppose the true error is greater than epsilon. So what is the minimum probability that all m samples are correctly labeled with probability? All L samples are correctly labeled. That means error is greater than epsilon, and it is not minimum. It is basically the maximum probability, because now the idea here is that all m samples. So one sample which does not satisfy by the, not satisfied by hypothesis, the probability is epsilon. Suppose we take the minimum case of error epsilon. So the maximum probability that the sample can be correctly labeled by that hypothesis is 1 minus epsilon. So now if all m samples are going to be satisfied with that hypothesis of your training set, of course, that covers the whole training set, then that should be 1 minus epsilon to the power m. I hope it is clear to you. Okay. So in that case, and you consider that in your hypothesis space, so there are k such hypotheses. There are k such hypotheses whose true error is greater than epsilon. So in that case, probability of choosing any hypothesis from that in that k, which will have this property that it would become consistent, but its true error is greater than epsilon. So that would be k into 1 minus epsilon to the power m, right? So that means that so there is a little bit of interesting simplification that is always carried out in this kind of analysis. One thing is that you know that 1 minus epsilon is less than e to the power minus epsilon. You expand the e to the power minus epsilon, then you can understand that 1 minus epsilon is less than e to the power minus epsilon. So naturally, k into 1 minus epsilon to the power m is less than k into e to the power minus epsilon into m, or less than hypothesis size of the, or since k is also less than, k is the basically number of hypotheses within the hypothesis space. So k has to be less than the total size of the hypothesis space. So finally, this probability that at least one of them would be consistent